Hello and welcome to this video about matrix proofs. In this video we'll prove that there is always a non-trivial solution for equations that have matrices with more columns than rows. But I'd like to prove this result first, that the solution sets for these two equations are the same. This proof wasn't split like this in the textbook, but I decided to split it up like this to make it more presentable and easier to follow. So now to prove this first part of the theorem, we have to get the matrix A into reduced row echelon form. We'll do this by multiplying A on the left by all of its Gaussian row operation matrices multiplied together. And we'll give this matrix a name, called the Gaussian elimination matrix, and we'll define a function that gets this matrix of A and call it GEM, which is an acronym of Gaussian elimination matrix. I'll just write all of this down more mathematically. When matrix A is multiplied on the left by all of these row operation matrices, we'll get the reduced row echelon form of A given by this function. We can set this function GEM to be equal to the product of all of these row operation matrices. I've already defined this function in a past theorem, theorem 1.9. So when we multiply A on the left by this matrix, we get the reduced row echelon form of A. We'll use this function to prove this theorem. We'll start with this equation. Then we'll multiply both sides on the left by this matrix called the GEM of A. So this matrix multiplies A on the left to give the reduced row echelon form of A, and on the right to give the zero vector, because a matrix multiplied by the zero vector will give the zero vector. I haven't proven it yet, but I hope to later. It's fairly obvious that it does, so I won't prove it for now. So that's it. GEM A is invertible because it's equal to the product of row operation matrices. This means that the solution sets for the vector x in these equations is the same. We can prove this result another way using a past theorem. We'll pack these matrix equations up into these augmented matrices. Then we'll use a past theorem to say that these two augmented matrices have the same solution sets, because they're row equivalent to each other. So let's start with the first equation. We'll pack it up into this augmented matrix. And we'll do the same thing with the reduced row echelon form of A. We'll pack it up into this augmented matrix. These matrices are row equivalent, because their parts are row equivalent. A is row equivalent to its reduced row echelon form, and the zero vector is equivalent to itself because of the reflexivity property. So from a past theorem, their solution sets are the same. So the two equations up the top have the same solution sets for x because of this. So we've proven part A a second time. So now to prove this main part of the theorem, part B, that if a matrix has more columns than rows, then there is a non-trivial solution to this equation, which means that there's a non-zero solution to this equation. So now to start the proof, we can already use part of this theorem that we've just proven to say that this equation has the same solution set as the above equation. So we can get the solution to the first equation by getting the reduced row echelon form of A, ref A, and substituting this in for A, and get the solution set of this second equation, which is easier to get. So a matrix in reduced row echelon form will have pivot columns and free variable columns, which makes it easier to see the behavior of the solution set. It must be noted that the number of pivot columns can't be greater than either the number of rows or columns of the given matrix. Because there are more columns than rows in matrix ref A, which is given in the statement of the proof, then there are more columns than pivot columns in ref A. So this implies that there are free variable columns in ref A, because they are the only other type of column in a matrix that's in reduced row echelon form. And the existence of free variable columns implies that there is a non-trivial solution for this second equation, and therefore for the first. So let's write this down more mathematically. We'll set this big green x to be equal to the solution set of this equation, and it's not equal to the trivial solution, which is the set that only contains the zero vector. So that's it, we've proven it. So let's look at an example of how free variable columns imply a non-trivial solution. Consider this matrix that has 3 pivot columns and 1 free variables column. We could then solve this equation for x, and it should give a non-trivial solution for vector x. We could easily get a solution for each free variables column. We'll set this column vector to be equal to all of the non-zero numbers in this column. Then we'll set the fourth number in this column to be equal to -1, because it's the position of the free variables column in the matrix. We can then check it for correctness. We'll multiply the top row in this matrix by this column vector, and the variable a, which can be any real number. So the 7 at the top multiplies by the first one in this row. The other numbers get multiplied by 0 and are therefore eliminated. Then the -1 on the bottom gets multiplied by the 7 in the top row of this column. So we're left with a 7 minus 7, which are the two numbers in the formula after we've eliminated all of the zeros. And then finally we're left with a times 0, which is always 0. So this is how free variable columns give non-trivial solutions. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.